Welcome to today's presentation of rigid pavement design. It has been prepared for you by Intelligent Concrete Incorporated, a research and development laboratory in Elbert, Colorado, specializing in making concrete stronger and lasting longer by bringing new and emerging technologies into the field. I'm your instructor today. My name is Paul R. Bryant, and I'm a professional engineer. I'm licensed in 5 states and have been a professional engineer since 1987. I specialize in geotechnical engineering, which is the study of soil mechanics and how soils perform or can be made to perform so that buildings and roads don't experience distress. I'm also a structural engineer. Structural engineering is the analysis and design of the things we build on top of soil. I have a bachelor's degree in civil engineering from California State University, Fresno, and a Master of Science in Engineering from the Air Force Institute of Technology. I held a variety of engineering jobs in my Air Force career prior to retiring as an assistant professor of civil engineering at the Air Force Academy. Following that, I've been in private practice as a professional engineer. It's my honor and privilege to be of service here today. This project is a result of a Phase 2 solicitation through AFWERX. Our mission is to not only provide an educational curriculum for the Air Force Academy cadets, but also to prove the efficacy of nanosilica, a concrete additive in concrete airfield pavements, which is a topic we will not cover today, but will explore in later modules. One of the first steps of this project is pavement design, specifically rigid or concrete pavement design. Asphalt pavements are known as flexible pavements, which might seem a little weird since a chunk of asphalt feels like anything but flexible. But in reality, these types of pavements function the way they do because they, in fact, move and flex a little bit and are actually self-healing under certain circumstances. These pavements will not be in today's presentation. In this course, we'll cover some of the terms common in pavement design, such as soil types, soil compaction as it relates to pavement design, base courses, subgrades, frost penetration, and others. We'll cover some very basic pavement design principles and perform a couple of actual designs. The purpose of this class is not to turn you into seasoned airfield pavement engineers, but to give you an exposure to the topic so that when you participate in the actual process of constructing a concrete pavement, you'll have a better understanding of the concepts and procedures surrounding pavement design and construction. Let's get started. In order to begin the design, we must first lay out the site where the pavement is to be placed. This specific pavement will be constructed outside the Field Engineering Readiness Laboratory on the USAFA grounds. Once we know where we'll be building, the next step is to discover the soil properties of the area in which we will be working. The first step of the design process for anything that will rest on the ground is the soil investigation. This process is to determine the properties of the soil upon which we'll be building. For larger projects, we will normally perform a dedicated soil exploration, using drill rigs to obtain soil samples from below the surface and laboratory tests to determine the soil's engineering properties. However, sometimes that process is not available to us and we have to resort to other means. In this case, we'll be using the United States Geological Service, or USGS, soil maps to determine the type of soil at the site. The striped box in the photo is our area of interest. You see the website for this service of the USGS listed at the bottom of the page. It's kind of fun to play with, and don't worry, you can't break anything if you visit the site and look around. Push some buttons, enter some addresses or locations, zoom in and out. If you have any interest in soil or geology, it's kind of a fun site. According to the USGS soil survey data, the majority of this site is comprised of Toma crowfoot loamy sands. There's a little bit of what's called kettle gravelly loamy sand shown in the area at the top right of the yellow box. Don't try to spend too much time to figure out how the geologists of the USGS came up with soil names like kettle or Toma crowfoot. They're often not very descriptive. The useful information is buried a little deeper in the soil descriptions. We can see much more of these characteristics as we drill down through the USGS material by clicking on a button or two. In order to know what kind of soil we're working with, we must first consider the soil characteristics. Let's take a look at what we have here. The soil we're working with is Toma Crowfoot Loamy Sand, meaning it is a combination of two soil types, Toma and Crowfoot. This chart breaks down the characteristics of each type, including its classification down at the bottom, which is probably the most important soil parameter for us in regard to pavement design. You can see the soil classification using the Unified Soil Classification System for the two types of soil is SM, which means it is classified as a silty sand. Briefly, clean soil, that is, one that does not contain organics or debris, consists of coarse-grained materials such as rocks, sand, and gravel, and fine-grained materials such as silt and clay. Silts and clays are both very fine-grained, like dust. Coarse-grained soils are inherently stable. Fine-grained soils are less so, and in many cases are completely unsuitable for construction without significant modification. Using the Unified Classification System, the designator for gravel is G, sand is S, C is clay, and silt is M. More than 50% of coarse grains would make it a sand or gravel, with silty or clay as modifiers, like silty sand or clay gravel, and so on. More than 50% fine-grained material makes the soil a silt or a clay, with sand and gravel being the modifiers, like a gravelly silt or a sandy clay. We can get really fancy sometimes with a silty, clay, gravelly sand, but we're not going to worry about that today. There are other types of soil classification systems, each created to fill a certain niche. Farmers like the USDA and the USGS method of describing soils with terms like loams. Engineers like the Unified Soil Classification System with terms like silty sand. Highway engineers like to use a system developed by AASHTO, which is the American Association of State Highway and Transportation Officials. But that organization doesn't provide the online resources like the USDA and the USGS, so we won't use them today. Oddly enough, the USGS and USDA, who provide a great deal of the available online soil information, use terms like sandy loam and clay loams and silt loams, but we as engineers like to use terms such as sand or silty sand or clayey sand, which are from the Unified Classification System, which is another government project through the ASTM, or American Society of Testing and Materials. You'd have thought that the USGS, the USDA, the USCS, and AASHTO would have talked with each other, but I guess not. As soil engineers, we deal almost exclusively with the Unified Classification System. Highway engineers use AASHTO, and agricultural engineers, also known as farmers, use the USDA methods. Regardless of which method is used, be it using online references or site-specific soil investigations using drill rigs and laboratory tests, it's very important to have knowledge of the soil conditions for the site where we're working. We can also see some typical characteristics of these soils. Note that they are very similar in makeup. Also, be aware that the depths of the various layers should not be taken as exact, but as indicators of general trends. In this case, both soils are expected to possess at least 5 feet of sands of various types. They are well drained, which means they do not hold water for long periods of time, which is a good thing for construction. The runoff class of medium refers to the characteristics of how excess water runs off and is not important at this level of pavement design. A classification of medium is typical of sandy soil. The depth to restrictive feature and water table means that restrictions like bedrock and the water table are at least 80 inches below the ground surface. The hydrological soil group is not too important to us for this project, but is a general categorization of soil based on depth of soil and the overall ability of the soil to accept water from any source. It's a little different than the runoff class, but is not relevant to our work here today. The things that we take away from this chart are that the soil is fairly deep before we get to bedrock and a water table, that it is well drained, meaning we should not have any trouble with wet soil, and that it's a silty sand. the abbreviation SM at the bottom, which means that it's more than 50% sand, and that it's categorized as a loamy sand. What does that mean to be a loamy sand? Remember just a second ago when we said this Toma crowfoot soil was called a loamy sand? This page shows the USDA, United States Department of Agriculture, soil texture triangle. This triangle breaks down the percentages of clay, silt, and sand contained in our soil, which is helpful since the designator SM only says that it's a silty sand, meaning it could be up to 49% silt and possibly even contain some amount of clay. How this chart is used is that a person would look around the triangle to find their soil descriptor. Its location on the chart gives the various percentages of sand, silt, and clay. As you can see, our soil is 70 to 85% sand, 0 to 15% clay, and 0 to 30% silt. In the end, the percentages all have to add up to 100%, of course, but these ranges of sand, silt, and clay result in the soil being referred to as a loamy sand, which for construction purposes would be considered a good quality soil, all other things being equal. Don't spend a lot of time trying to figure out exactly how to use this chart, but there are some very quick tutorials which can be found by looking up USDA Soil Texture Triangle. Design parameters for the soil at the site can also be determined by soil testing conducted for the particular project. This method often provides much more accurate data as soil type can vary greatly from one site to another site, even just a few hundred yards away. If you remember a few slides back, very nearby was a soil listed as a kettle gravelly loamy sand, meaning it contains a significant fraction of gravel, which does not appear to be present at our site. The takeaway is that soil types can and do change dramatically over even a short distance. Sometimes several different types of soil intersect and overlap at a building site, further compounding potential design and construction issues. Today, though, we don't have to worry about that. A lot of times, though, it is not possible to perform a site-specific soil test using a soil drilling machine and running the soil samples through a lab to determine their characteristics, a process that can take a week or more. Using soil maps and classifications can be a quick and often reasonably accurate way to estimate the soil characteristics, at least for planning and estimating purposes. This method will be considered as adequate for purposes of this class. Some critical characteristics of the soil which must be considered are known collectively as Atterberg limits, which are called the liquid limit, the plastic limit, and the plasticity index. Whenever a soil is known to have a significant percentage of silts and clays, more than 20 to 30% depending on the proposed construction, these tests should be run, regardless of the source of the soil composition data. They can be performed rigorously in a lab using specialized testing equipment or can be estimated in the field using only one's hands and an accurate scale. These Atterberg limits are some of the things that a site-specific soil test would provide to us. For our class, we are just going to be assuming the values based on our soil types and a general knowledge of the characteristics of this type of soil. So what are these Atterberg limits and why are they so important? The liquid limit is the percent moisture that causes a soil sample to turn from a plastic consistency that is able to be formed into a narrow cylinder or a thin ribbon by rolling or pressing between one's fingers into a liquid like mud, and the whole thing falls apart. The plastic limit is the percent moisture that causes a soil to change from being a friable solid, that is, it breaks apart under pressure, to being a semi-solid that you can start the process of being able to mold and remold. Imagine that you've got a little bit of soil in your hand and you're working it with your fingers, trying to get it to form into a cylinder or a ribbon. You keep adding water to it, a couple of drops at a time. You'll feel the soil gradually start to begin to be able to be molded and remolded instead of just breaking up. Some soils will do this readily, others not at all. They just go from being a crumbly soil to being mud without an intervening plastic state. Once you've gotten a so-called plastic soil to be able to be deformed into the ribbon or cylinder, and you keep adding water, the soil will begin to lose all ability to hold its shape and will begin to be mud. By weighing the soil and the amount of water added, it's possible to estimate those two parameters. This brief description won't make soil scientists out of you, but if you remember that good soil engineers always have a bunch of tools in their engineering toolbox of tricks, that's probably enough for now. Anyway, the plasticity index is simply the difference between the two moisture contents. A low PI or plasticity index of less than 10 or 15 means the soil will change fairly quickly from being stable, that is not plastic and not liquid, to completely unstable, that is liquid or mud, and not spend too much time, that is a narrow moisture range, of being in the relatively unstable plastic range, where deformations of the soil will readily occur. Some soils never exhibit a plastic state. A high PI, say greater than 20 to 25, indicates that a soil could be much more susceptible to instability over a much greater range of soil moisture contents. Just remember this: a high plasticity index is bad, a low plasticity index is better. The Atterberg limits are only performed on the silt and clay fraction of a soil, so the amount of sand when combined with the Atterberg limits tells an engineer if trouble might be brewing. In our case, because we have relatively low amounts of silt and clay, a higher PI, plasticity index, could be considered acceptable because there is a lot of sand present to carry the load. Sand, by definition, has no Atterberg limits, and it is what contributes the most to a soil's structural stability. Whereas if a soil has a greater percentage of silt and clay with little sand to carry the load under high soil moisture contents, a much lower PI would be required. Again, don't fret too much about how all this works. Soil mechanics at the most basic level is a semester-long class. Here today, just remember that a low PI is good and a high PI is not good. Any PI above 20 should be evaluated on a case-by-case basis by a soil engineer relative to the specific project. Here are a few more definitions and the values we have assumed for the liquid limit, the plastic limit, the plasticity index, and the soil moisture content parameters. As definitions, base course is a layer of soil constructed just below the pavement, and it is extensively compacted and tested to ensure a very high degree of soil density. Highly compacted, very dense soil does not accept much water into it. Soil with too much water will quickly lose its structural capacity. Remember how we just talked about this with the Atterberg test and how a soil can turn plastic and unstable with moisture? Sometimes the base course is comprised of soil imported to the site because the native soil is not considered to have sufficiently high structural capacity. A subbase is a layer of soil that's built under the base. It's often made up of native material that is moisture conditioned, meaning water is added or water is allowed to evaporate, and then recompacted in thin layers, usually about 6 or 8 inches thick each, but usually at a lower density than the upper base course layer. Subgrade is the native soil. About the only thing we ever do to the subgrade is to roll it out smooth and flat and fill out or compact any low or loose areas. We dig out undesirable materials like rocks, stumps, or pockets of clay. Sometimes we'll scrape it up a little bit, add a little water, or let it dry out and roll it out flat again. But usually we don't do a lot to the subgrade. Because we are designing this pavement in Colorado, where freeze-thaw damage is prevalent, we must prepare a certain depth of soil below the pavement to protect it from frost according to the Uniform Facilities Criteria Manual. We'll talk about frost protection in a minute, but you can see a link to this manual if you want to look it up or if you're having trouble sleeping. In cases where the soil at the site is not well draining, sometimes a drainage layer or a structure is required to be placed under the pavement. This is such an extensive field of study, we won't get into it today. In our case, even though our soil is well draining, It doesn't mean that frost can't or won't be a problem. We'll poke around this subject in a few minutes. First, we need to talk about a few terms that are typical in pavement design and construction conversations. Soil compaction is the process of compressing the soil to force out air and, in some circumstances, excess water. Compacted soil is much more stable than uncompacted soil, as pressure forces out air, making the soil more dense, and compact meaning additional compression or settlement is difficult to occur. The percent compaction relates to how close to a theoretical maximum degree of densification that can be achieved. Typically, it's expressed as a percentage of a Proctor density. Proctor densities are tests that are performed in a specific way against known parameters to give a standard measure of how dense a soil is. Buildings usually use what's known as standard Proctor, and 95% density is a typical specification. Roadways and pavements usually use a modified Proctor density, which provides a higher degree of compaction, and again, normally 95% is the minimum specification. Don't worry, neither of these will be on the test. A minimum depth of compaction is a function of how deep we must go into the subgrade, that is, the native undisturbed soil, with constructed layers of densely compacted structural layers of soil built on top in order to achieve a stable surface upon which we can build our pavement. Now it's time to talk about a term called K, the modulus of subgrade soil reaction. This value of K is used throughout the entirety of pavement design, and it is very important. In its most basic form, it's a standardized measure of the strength of the native soil. High numbers are good, low numbers are not as good. The K of a native undisturbed soil can often be improved simply by scarifying, that is, digging it up a little bit, moisture conditioning, that is, adding a little water or allowing a soil to dry, and recompacting using proper machinery and techniques. For light-duty pavements, often this is considered adequate soil preparation prior to pavement placement. The table shown uses soil types and moisture contents in percentages to estimate the K value. Tabular values are often good enough for estimating purposes and for designs of less critical surfaces or if laboratory testing isn't available. Critical pavements, especially those that are very extensive in scope, such as an entire runway, require laboratory tests to determine this value. Our modulus of subgrade soil reaction here is 150 pounds per square inch per inch, which is often abbreviated PCI. That looks a lot like pounds per cubic inch, but it's not. It's pounds per square inch per inch of depth. This won't be on the test either. Just remember that low numbers are bad and high numbers are good, the opposite of golf. Here's a chart that shows a correlation between the K of the native soil and what happens to it when it is purposely recompacted. Along the left side of the chart is the K of native, that is, the existing undisturbed soil, and along the bottom is the depth of compacted soil in inches. Our soil has a K of 150 PCI, an assumed value based on these tabular values typical of the soil type. Find along the left side the number 150 and you'll see a curved line coming off of it. Go along the bottom to 34 inches and then go up to the 150 line. You'll see that our K has been increased to perhaps 400 PCI or thereabouts. Remember this number for about 15 minutes. We'll be using it later. The pavement designer will have to determine whether to build on native soil, which can often be the case if the pavement is not required to be in demanding service, or if it's necessary to dig out some soil and recompact it, or even dig out soil and replace it with better quality materials. Some soils, like heavy wet clays, can't be made to perform adequately without replacement with better materials, sometimes down 2 or 3 feet or even more. The airport at Dallas-Fort Worth, when it was built, required 10 feet or more of the native clay be dug out, The soil extensively modified both chemically and physically and recompacted. Many of you know the size of DFW's airfield pavements, so you know this had to have been a gargantuan undertaking. And of course, if you've used DFW lately, you know that many of the airfield surfaces are really starting to show wear. A complete rehabilitation is planned, but the cost is so extreme, no one is quite willing to pull the trigger on it yet. Other measures like adding synthetic reinforcing blankets between layers of compacted soil or making a base layer of heavy rock followed by several feet of compacted good quality soil can also be used. Remember, this class is a 30,000-foot view of rigid pavement design, so we won't be getting into the art and science of soil modifications for pavements. Just know that for every problem we might encounter in designing pavements, we probably have a solution. Many of them learned the hard way, such as the DFW runways and taxiways. Speaking of learning the hard way, I know we're covering a lot of different topics, maybe none of which really seem to be related directly to pavement design, but I promise you, we will get to that in just a few minutes. We need to include a few other things along the way so that when they come up in the design process or when we're actually building out in the field, you'll know what we're talking about. A very important element of any large pavement, say larger than 15 feet in any direction, is the subject of joints in the concrete. Joints, as the slide says, are provided to permit contraction and expansion of the concrete resulting from temperature and moisture changes, to relieve warping and curling stresses due to temperature and moisture differentials, to prevent unsightly, irregular breaking of the pavement, and as a construction expedient to separate sections or strips of concrete placed at different times. The three general types of joints are contraction, also known as control, construction, and expansion. This graphic shows a number of the elements of a typical pavement, including the joints. Concrete pavement contains joints to prevent or control cracking, shrinking, and curling. Essentially, they allow the concrete to move, thus preventing or at least lessening damage. But if not properly designed, joints can actually cause problems instead of fixing them. You've all experienced the bump, bump, bump of riding along a freeway in a car or a truck. These bumps are the result of inadequate pavement design and in particular, inadequate joint design. In the old days, concrete pavements were placed without reinforcement and without any attention to joints. That was okay back then because traffic counts were much lower and vehicle weights and speeds were much less. Even today, with modern pavement design, due to increases in traffic and vehicle weight and speed, even newer pavements experience joint failure due to overloading causing the bump, bump, bump that you feel. In this slide, we can see a lot of elements, some of which we've talked about, the pavement, the base and subbase materials, and the subgrade, but we also see the joints. Also, as a part of pavement design, but not really a part of today's discussion, are of pavement's surface texture, such as, is the pavement grooved to aid with water dispersal? And how is the pavement finished off, which affects how smooth the pavement feels? How smooth the pavement feels is also a function of how fast is the vehicle. A pavement that feels fine at 60 miles an hour in a car might feel completely unstable at 150 miles an hour in a jet. Joint placement and performance are very important to maintaining a good surface smoothness, but it's just one part of the design and construction of a successful pavement. The combination of joint design and placement and what kind of surface texture is constructed can make or break a pavement design, regardless of the structural performance of the pavement. There are multiple types of joints in concrete pavement, and they serve different purposes. This slide highlights the three main types of joints and what they are designed for. Contraction joints, also called control joints, are those joints that you see that are either tooled into fresh concrete using a specialized jointing tool or cut in a few hours after the concrete is placed, literally as soon as a concrete saw can be operated on the surface without damaging it. Joints do not go all the way through the thickness of the slab, but rather only about 1/4 of the depth or less. They serve only as a weak place in the concrete where cracks can occur and then later be sealed up. Cracks will occur as a function of the concrete curing. They are unavoidable in any pavement larger than about 20 feet or so in either direction. As the water in the concrete mix is used up by the process of hydration or curing, the concrete shrinks a little bit. A small pavement, say a little patio behind your house, might not shrink enough to need any joints. But as concrete cures, it can shrink as much as a half an inch or more in 100 feet. Because concrete is so brittle and has relatively poor tensile strength, that is, the ability to resist being pulled or stretched, as opposed to being pushed or compressed, which is known as compressive strength. This shrinkage shows up as jagged cracks every 15 to 20 feet along the surface. If we put in a weak place like a joint, the cracks will tend to localize within the joints and not out in the main body of the pavement. Later on, we can seal the joints and their cracks with a sealer and we'll be good to go. When building a pavement, there will be only so much we can do in a day. So construction joints are placed between successive pieces of work. Construction joints are usually spaced to line up with our contraction or control joints, so they are usually not a visible component after construction. Expansion joints are used when a pavement butts up against something that is not a pavement, or perhaps another pavement going in a different direction. Manhole covers, for example, will have a semi-flexible ring of material around the steel collar to provide a little bit of give between the concrete and steel, or there would be a much greater chance of pavement failure at that point. The same is true where one pavement intersects with another pavement or a building. We have to build in a little band of flexibility or something is going to break. Our pavement will be designed with transverse joints at 10 feet spacing with slip dowels to hold these slabs together. We'll talk about this a little more in just a second. You might be thinking, why don't we just put in a bunch of reinforcing steel into the concrete and avoid a lot of problems? One advantage of heavy steel reinforcement is that joints can be placed at dramatically greater intervals, and damage to the roads due to poorly performing joints isn't really much of a thing. We can do that, and we have done that, and we now know that reinforced pavements are not always a good answer. CRCP means continuously reinforced concrete pavement, and it's when we install a mat of steel both lengthwise and crosswise in a pavement. This is a great way to make a pavement really strong and capable of resisting tremendous loads. It's also very expensive, and when the day comes when the pavement finally has to be demolished, it makes for a nightmare for the demolition crew, as the steel continues to perform its job of holding the concrete together. Crews must use torches or other means to cut apart the steel holding together the shattered sections of concrete, a process that is dangerous and very time-consuming and expensive. It also renders the demolished concrete unfit for reuse, and it must all be thrown away. Unreinforced concrete is amenable to quick demolition, and the demolished concrete can be run through a crusher with the resulting material reused in new concrete or in the design and construction of base and subbase layers. This schematic illustrates the types of reinforcement typical in a concrete pavement. The slide shows 4 inches of ACP base. ACP is asphalt concrete pavement, and it's not part of this discussion. It's just another type of base course preparation typically not used in airfields. Contrasted to continuously reinforced concrete pavement, most concrete pavements are constructed as unreinforced, using only dowels to help transfer the load from one slab to the next. They are placed exactly where the contraction joints will be installed, and they serve as structural bridges across the inevitable cracks that will form at these joints. Our pavement's reinforcement will consist only of dowel bars joining the slabs. In the construction process, the dowels are held up by little baskets in order to place them in the correct location, typically at the middle of a concrete pavement. Okay, so why do we need dowels again? The important functions of dowels or any other load transfer device in concrete pavements are to help maintain the alignment of adjoining slabs and to transfer some stresses from loads from the adjacent slab, thereby limiting or reducing stresses in the loaded slab. What this means is as the load on the pavement, such as a wheel load from a truck or an airplane, goes from one slab to the next across the contraction or control joint and the crack that is also there, remember, this crack will go all the way through the entire depth of the slab. The load passes from one slab to the next. This load transfer from one slab section to the next functions really as an impact load. Very small at first, but think about all the times it has to happen. On a freeway with millions of vehicles, it's a constant process. On an airfield, there will be fewer vehicles, but they are typically much heavier. If the only thing holding the crack together is friction between the two sides of the crack, it won't take long before wear starts to occur, and with wear comes a loss of the ability to transfer the load across the crack, and the constant impact loads can gradually start to pound away at the soil and pound away at the concrete, grinding both down just a little bit, causing settlement and distortion of the pavement surface. And there's your bump, bump, bump. Minor deviations are not so bad, but once the offset gets more than, say, a 1/4 inch, they can be really annoying. When they get over a 1/2 inch, vehicle speed and control are affected. California's Highway 99 between Bakersfield and Fresno had drops of more than an inch before renovations were performed. Fortunately, we don't have to work too hard to figure out the dowels. Through a combination of scientific analysis and practical experience, we have available tables that help us with dowel selection. Dowels are typically smooth, not like rebar, which has a deformed surface, because we don't want them to transfer any tension across the joint. In fact, many times the dowels are coated with a thin layer of grease to prevent any adherence of the concrete to the dowel. You can see at the bottom of the chart, extra strength pipe, if it's used, must be plugged or filled. This is to prevent any concrete from getting into the pipe and somehow using that inner surface to bond everything together, and potentially allowing tension to be transmitted across the joint. We do not want tension to be transferred. We only want shear or strength in the vertical plane. We can use this chart to determine the minimum dowel length, maximum dowel spacing, dowel diameter, and type. With the assumption that our pavement is 8.5 inches, our minimum dowel length is 16 inches, our maximum dowel spacing is 12 inches, and our dowels will be 1 inch in diameter. I promised we'd get to this. Another component of pavement design is whether or not we must account for frost. In most parts of Colorado, we do. At the Air Force Academy, we do for sure. Frost can affect structures because frozen soil, if it contains too much moisture, will heave or swell. It may not seem like it would be that much, but the swelling pressure is intense, about 30,000 psi, with 5 to 9% expansion of the water, and it's capable of splitting solid granite rocks. Competent granite is much harder and stronger than concrete, and if water can reduce a mountain to gravel, it sure as anything can tear up a concrete pavement. Freezing water in joints will damage pavements quickly through a process called spalling, but more to the point, freezing water in soil will cause it to expand and lift a pavement. When it melts, it can leave a void space behind, meaning there's a weak place under the concrete and a place where even more water can accumulate, causing even more damage the next time it freezes. A weak support location means that under heavy load, a pavement is much more likely to fail in that area. In order to design for frost protection, we must determine the frost group our soil falls into. Since our soil is a fine silty sand classified as SM, our soil's frost group is F4, and this is the most frost susceptible group. Fortunately, we have straightforward methods to mitigate this kind of frost damage, and we will get into that in a few minutes. For now, though, we're going to start with a basic rigid pavement design. I promised we'd get to this. Another component of pavement design is whether or not we must account for frost. In most parts of Colorado, we do. At the Air Force Academy, we do for sure. Frost can affect structures because frozen soil, if it contains too much moisture, will heave or swell. It may not seem like it would be that much, but the swelling pressure is intense, about 30,000 psi, with 5 to 9% expansion of the water, and it's capable of splitting solid granite rocks. Competent granite is much harder and stronger than concrete, and if water can reduce a mountain to gravel, it sure as anything can tear up a concrete pavement. Freezing water in joints will damage pavements quickly through a process called spalling, but more to the point, freezing water in soil will cause it to expand and lift a pavement. When it melts, it can leave a void space behind, meaning there's a weak place under the concrete and a place where even more water can accumulate, causing even more damage the next time it freezes. A weak support location means that under heavy load, a pavement is much more likely to fail in that area. In order to design for frost protection, we must determine the frost group our soil falls into. Since our soil is a fine silty sand classified as SM, our soil's frost group is F4, and this is the most frost susceptible group. Fortunately, we have straightforward methods to mitigate this kind of frost damage, and we'll get to that in a few minutes. For right now, we're going to take a little break before we start on the actual process of designing concrete pavements.